Okay, we are 1 minute after the hour, so why don't we go ahead and get started? Welcome to the Air Sea Fluxus from Space webinar series. Today, Simon Josey from the UK National Oceanography Centre in Southampton is going to talk about record winter 2023 Antarctic sea ice decline, increased ocean heat loss, dense water formation, and storms.
Thank you, Sarah. Let me start the slideshow. Wow, and that was quite a long title, wasn't it? So I need to maybe make it more short for future talks. Great. It's lovely to be here and to talk on this topic and to talk on the Southern Ocean. And this kind of reflects some work I've been doing over the last a year and a half, I guess, with Andrew Myers at BASS and several people at British Antarctic Survey, I should say, and several people at the NOC in addition to myself. That's Adam Blaker, Jeremy Grist, Jenny Mecking, and Holly Ayres. And we're very interested in the very low winter ice cover values in 2023. That caught my eye, as it did many people's as soon as it happened. And of course, there's question marks about why it happened, what were the drivers, but that's not really what I'm going to talk about because my perspective is more what are the impacts. And being an air sea interaction guy, and this being an air sea flux seminar series, I'm going to focus on that, but also extend that and talk about impacts on the ocean as far as we can get them in terms of dense water formation and also in terms of impacts on storms. Now, before I go any further, I'm just going to shrink that. Oh no, what's that done? Hang on a minute. Okay, now I'm okay. Right. I can't see anybody now, but that's probably a good thing. I can see all my slides instead. And you're probably also seeing that. Okay, so it should look good now. Just shout, obviously, if you can't, if something goes wrong with the slides. But what we're looking at here is, first of all, a picture, the figure B on the right-hand side. Can you see my cursor, by the way?
Yes, looks
Yeah,
great.
great. So the cursor, I'll come back to the figure. I'll come back to in more detail, but this is for the winter heat flux anomaly in 2023, and you can see large areas of blue and purple outlined with these black boxes. These are regions of very strong increase in heat flux. That's a 60, 70, 80 watts per square meter increase in heat flux, averaged over a 2-month period compared to the climatological mean. That's a strong signal. And then there's just a pretty picture which my colleague Andrew Myers provided to lend some interest to the slide. So let's do a bit of background. And you're probably all aware about the longer term history of Antarctic sea ice decline. And that's nicely encapsulated in this paper from a couple of years ago now by Purick and Doddridge. So what we're looking at here is a time series of sea ice extent anomaly, and Antarctica, or the sea ice region, bucked the global trend of changes in line with the climate crisis for many years, from 1980 through to about 2016. We saw, this must be the satellite record, a gradual increase in the Antarctic ice extent rather than the decrease that people were expecting. And that was a puzzle for a long time. But then there was a sharp change in 2016. This was the first occasion where we had a very sharp summer melt exceeding the climatological limits. This is December 2016. And then low values thereafter, perhaps some partial recovery. And then another summer melt event in January 22, and then into 23. And then that primed us for the strong losses or the failure of the ice to regrow in winter 2023. And that's what we'll be talking about. And at the same time, of course, over a more limited time period, essentially post-Argo, I guess, the Southern Ocean temperatures have warmed in at least, as this figure shows, in the upper 600 meters or so. And then just to put 2023 in context, this is a further figure from Purick and Doddridge, and it's basically showing the seasonal variation, so January through to December for all years from 1978 onwards, becoming increasingly going from blue to orange as time progresses. And we can see that what happened in 2023 starting in about March, April time. That's important. You'll see, we'll go back to that in a minute, but starting in about March, April time, really diverged from the previous cloud of events. We had this major anomaly in the sea ice. I won't say reduction in sea ice because it was a failure of the ice to regrow, but compared to the longer term mean, it's a reduction, I suppose. And it ended up at about 2.3 million square kilometers below the average, and that's twice as large as the previous record. So a little bit more background. So in quite a few papers on the summer 2022 event, as I said, prior to the winter 2023, most of the previous events were occurring in summer. I just picked one of the papers out there, quite a few out there. This is by Yadav et al. And I picked this one because it talked about the atmospheric drivers to some extent. So the color here is showing the anomalous sea ice extent, and it's making the point that the anomalies actually started in the spring of 2021, so September, October, November 21, and the blue colors are strong reductions in ice extent. I guess this is percentage there, not sure. And that continued through into the summer, but these authors make the point that this was accompanied by anomalously northerly winds. So if we look in this region in particular, and in other regions as well, so we have anomalous warmth being brought into these areas, and they argue that's what's melting the ice, and there's a large contribution to that. And in many of these events, there's this tension between how much has the atmosphere done and how much has the ocean done in terms of warm ocean temperatures, melting the ice or preventing it from growing, as opposed to melt from above, or minimization of heat loss, preventing the ice regrowth. And I think that's still an open question in many cases. So let's come on to this paper, which we had, came out just before Christmas. Yes, so to start with, of course, we looked at the ice cover. This first figure was not something really new. It was the sort of driver for the rest of our analysis, but it captured the reduction in ice cover at the peak of reduction. We chose to look at June, July 2023, partly because we were looking at it as it was ongoing, but this is when the signals were strongest. And you can see the strongest signals in the Bellingshausen Sea here. The outer Weddell Sea, for want of a better name, just called this the Northern Weddell Sea. You can argue about what it should be called, but that's how it's referred to. And also here, it's the edge of the Ross Sea, but that's another area of strong ice decline. And there's a weaker region over here, which we just referred to as Enderby, because that's Enderby land for the purposes of the analysis. So we found that the ice concentrations here, so this is looking at ERA 5, but in ERA 5, it's a satellite-based boundary condition data set. So this is satellite data for the sea ice cover. The ice concentrations reduced by up to 80%. And here we're looking at the ERA 5 heat fluxes, and those heat fluxes are reduced, are strengthened, I should say. So my sign convention throughout is that heat gain by the ocean is positive, heat loss is negative. So negative values, negative anomalies imply stronger ocean heat loss than normal. We can see particularly strong heat losses in these regions. And we've tried to do some sensible averaging by defining boxes which encompass each of the regions, Weddell, Bellinghausen, Ross, and Enderby. And you'll see more on that as we go along through the analysis. So before going a bit further, though, there's a couple of papers which caught my eye or pointed out to me subsequent to our publication of R1. So I just want to draw attention to this one, which you may have heard about already. I'm not sure, by Zach Espinoza, if I can remember correctly. And this was a nice study using the Community Earth System model of the drivers of the 2023 winter anomaly. And here this analysis comes down on the side of the ocean and carefully says and finds that about 70% of the sea ice anomaly is driven by warm Southern Ocean conditions. And we can see that the top plot here just gives some idea of how well the model's doing compared to observations. So it's doing a pretty good job of capturing the sea ice concentration variations, it's doing a good job. Well, a reasonably good job of capturing the SST. This figure troubled me slightly because the SST anomalies in the model are quite a lot stronger than those in the observations, but not sure to what extent that affects their conclusions. And you don't need to worry about the bottom one too much. It's just showing the change in those values for each of regions, several regions they've defined, but we can see the declines there. But the point is that this study finds the 2023 sea ice anomaly was due to warm ocean conditions. But then, there should be another slide there, but it seems to have disappeared. There's actually, it's back one, isn't it? Why is it going like that? Okay, here we go. There is another study by Ionita et al., or I think it was just Ionita, and they find the converse, but the anomaly in winter 2023 is mainly due to advection of warm air over these regions. So as I say, the jury is still out on the relative contributions of ocean and atmospheric forcing to this record low winter values. It's a kind of justification slide. I guess I don't really need this here, but why is the ice decline of concern? Well, it's the whole load of reasons why it's of concern. For example, the ocean warming, as well as melting the sea ice, can then impact on the land fast ice. So we have ice shelf melt, contributions to sea level rise. So that's a huge concern. There are concerns about the southern ocean carbon sink, paper by Elizabeth Shadwick, which I picked out, I think based on observations, in fact, at a point location in the West Antarctic Peninsula with some mooring data, I guess, looking at air sea CO2 fluxes and a seasonal cycle. And if you focus on the red line, that's pretty much, I think, the combination of air observations and probably a bit of modeling as well, but taking the sea ice into account. So we have ocean uptake of carbon in the summer months, and then and then in the winter months we have the ice cover preventing the ocean from outgassing that carbon. But if we take the ice away, as they did in their analysis, then we see a strong outgassing in the winter. So there's a concern that if we reduce the sea ice, that will allow additional outgassing in the autumn and winter, and that'll weaken the Southern Ocean carbon sink. And then talking to various biologists and so on here and looking at studies in the literature, of course, there's a range of ecological impacts as well. Penguins are an emblematic species, emperor penguins, and there are studies which are showing that there are impacts of the ice decline on the colonies of penguins, potentially leading to colony extinction. So there's a whole raft of concerns there, and one or two others, which maybe I'll come on to later in the talk. So let's now look at the results of our analysis in a bit more detail. I've already shown you the figure on the right-hand side. This figure is in the supplementary to the paper, puts it in a bit more context. If we take these four boxes with the strongest ice reductions and the strongest heat loss changes, and we plot them up year by year, using the black symbols here for the winters from 1990 through to 2015, and the blue symbols for 2016 through to 2022, we can see just how much off the charts the 2023 conditions were. There, this red square down here, way outside the previous variation of sea ice concentration with heat loss. Or I should say the other way around, way outside the increase in heat loss as the sea ice concentration declines. Okay. Now, in doing this, we have to worry about the choice of reanalysis, obviously. As everybody knows, air sea fluxes are notoriously hard to obtain reliably, and that particularly applies to the mean state, where differences between the terms can lead to imbalances in the mean of 20, 30 watts per square meter, which are difficult to resolve and persist at climatological timescales. But in contrast to that, when you look at a very strong event, it tends to be the case that there's better agreement between the reanalyses, and that's the case in this situation. So this is the figure you've already seen using ERA 5. It's the heat flux anomaly in winter 2023. If you go to another reanalysis, MERA 2, then you see a very similar pattern indeed, perhaps with slightly stronger heat losses. And if you go back in time, these are the data sets I had available for this plot to NCEP, which we were using 15, 20 years ago now. It's coarser resolution. What we see there is that we again get a similar pattern, but a bit more blocky because of the coarser resolution than the other two. So we think these patterns are robust to a choice of reanalysis, which is gives us extra confidence in the analysis. You need to remember what the actual mean field looks like. It looks extremely dramatic in the anomaly field, and those numbers are large in terms of the anomalies. If you look at the actual heat flux itself, this is the heat flux pattern, the climatological mean for 91 through to 2020, and this is the corresponding pattern for 2023. And we can see this incursion of blue and purple values there. This is the stronger heat loss because of the reduction in ice extent. And if you take an example value, so this green circle here, it's not a mooring or anything like that. Don't get excited. It's just flagging a particular location. If we look at the values there, the heat loss has more than doubled from 57 watts per square meter on average for 2090, actually it's a slightly different period, 2015, to minus 132 watts per square meter in that winter. So a huge increase in the heat loss to the atmosphere. Now, a bit of decomposition. What we did here was just to ask the question, what was the contributor towards these extreme heat loss values? And there's also a slightly different way of representing the data you've already seen as well. So the sea ice concentration averaged over those four boxes that I talked about before is now shown for the earliest period, black, the intermediate period, blue, and then the huge reduction in 2023. Likewise for the net heat flux. But then if you break it down into the components, the latent, the sensible, the long wave, and the short wave, you can see that the latent and the sensible both increase significantly in winter 2023, whereas the radiative terms, perhaps unsurprisingly, and shortwave's actually up here because it's winter, there's hardly any shortwave. So it's all down to an increase in the turbulent heat loss, the combination of sensible and latent heat fluxes. And it's also important to remember that, of course, we like to work with monthly means, but that sometimes conceals the strength of the anomalies on daily timescales or shorter timescales, and it's those stronger anomalies which can be important for example, for initiating ocean convection or for provoking a response in the atmosphere. And so this shows, looking at all grid cells within those ice-affected regions, the change in the heat flux as a distribution, and the blue and the black lines being the early periods are fairly close together. But the red line is again a lot different. We see a big increase in the number of high heat loss events, and you can quantify that in various ways. The number of heat loss events, for example, which are stronger than minus 100 watts per square meter on a daily basis, double between these earlier periods and winter 2023. The interquartile range, which is shown here, has strengthened quite significantly as well. And yes, I've mentioned the need to consider these extreme values for their potential impacts. Okay, and then the phase shift. So this was as the second part of the analysis. We were worried about not worried, we were interested in the seasonal cycle, and this then touches on drivers of these events. So what we see, if we plot the seasonal cycle up, averaged over the four regions we talked about earlier, the black and the blue lines are what we're seeing for these earlier periods. And then if we look at 2023, the difference is, well, there's a couple of differences. The most obvious one is that the peak in heat loss has undergone something of a shift. It's about a month or more than a month later in the season than it was before. But I think the most interesting thing here is the fact that if you look at the heat loss, what normally happens as you come out of March and into April is this, or into March and April, this heat loss is strongly increasing. And this is what's causing the ice regrowth. But in this particular year, in 2023, we had a failure of the increase in heat loss. So what we're seeing there is the um, weak heat loss conditions, and those weak heat loss conditions, when you look at the sea ice concentration, we're suggesting that the part of the reason why the sea ice didn't regrow is it wasn't it didn't the ocean surface didn't experience the heat loss that it normally does to the atmosphere, um, and that will favour a slow rate of ice regrowth. Now, putting that in context, we weren't, as I said, we weren't really looking at drivers, but this is just one aspect of what is a complex, probably a complex set of drivers. But if we look at this April period and we ask what the atmosphere was doing in that period, that's what we're seeing here. And here I've actually color coded the colors of the air temperature now, and we can see in the ice decline regions warmer air temperatures than normal, associated with northerly flow. So a bit similar in some ways to what happened in the summer 2022 event. Probably that change in atmospheric circulation has played a role in this. Now, I'm going to go on now to talk briefly about water mass formation, and I'm going to pause in a couple of slides' time just to have a quick break, ask for questions before the sort of second half of the talk. So if we'd like to know what the impact is on the ocean of this extreme heat loss, and we'd like to do a full water mass formation calculation. And I've done a fair bit of that in the subpolar gyre of the North Atlantic, but it's always been in the absence of ice. And of course, in this region, you have ice and you have ice formation and you have brine rejection. And that brine rejection is an important component when you come to look at water mass formation processes, thinking about the work of people like Abernathy et al. That we couldn't get reliably at the ice thickness, and so we couldn't do this part of the calculation. So at that point, I thought to myself, okay, should we not bother with this at all, or shall we try and do it just looking at the heat flux contribution to water mass formation? So this is not the full water mass formation plot; it's the heat flux contribution to that, and E minus P as well. That's in there as well. So it's the surface flux contribution. And what you're looking at on the right-hand side are density on the bottom and amount of water formed in terms of sphere drops in a particular density class. So it's 0.1 intervals in density here. And in each one of those, if we just look in particular at the Northern Weddell Sea and the range 27.6 to 27.7, you can see there are three different bars here, two very small ones, which was the amount of water formed due to surface fluxes in that density range in the early periods, but a very, very low amount. And then here is the amount in 2023. And for this, we're using the SST data. You need the density. We're using SST data set in ERA 5, which is satellite observations of SST. And then we also need salinity, which comes from the EN4 Argo-based data set. And that perhaps is something to think about. But the key point is, for each of these figures, we're seeing larger red bars than the other bars in the upper density ranges. We're seeing new water being formed, or a heat flux contribution at these densities, which has not occurred in earlier years. And so we think this will have an impact on the water mass which is formed. In particular, I kind of said this, but it's written in text here. This value here exceeds by a factor 10 what we had earlier in the period. And also, just to show a scatter plot again, to put it on, to make it easier to digest, this is the amount of water formed due to heat fluxes summed over all four regions we're interested in for densities greater than 27.6. And these are what we were seeing in the earlier years from 1990 onwards. And then suddenly in 2023, we have this much stronger heat flux and major increase in the amount of water being formed at the high density end. Okay. Now, there was a change of slide there. Now, if you blinked, you missed it because I've done the same thing again with MERA 2. Again, just to be careful and use a different reanalysis, and essentially you get pretty identical results. It's hard to see the differences between this plot and the preceding one. But you can, if you look closely, see there are some differences. So these results are not sensitive to the choice of reanalysis, but I stress again that you do need to worry about the missing terms, which we haven't included, which include brine rejection, etc. And then this is where my colleague Andrew Myers came in more. So I said, well, what are the likely impacts on the ocean circulation? Because I'm definitely not an expert on southern ocean circulation. I'm an SC interaction person. But as I understand, and this figure, I should say straight away, has come from an excellent review of Bennett et al. Late last or sometime last year. So this is showing the southern ocean circulation and fronts associated with the ACC. And we know we have these gyre structures in the Weddell Sea and in the Ross Gyre. And we can schematically overlay where we think this new higher density water is being formed. So that's shown there by those purple ellipses. And so the question for others to take up probably is what happens to this modified water? So as I understand it, the water mass out here, water mass is out here at the surface, sometimes called Antarctic surface water. And then sitting underlying those, we have circumpolar deep water, and then potentially mixing between these two water masses can modify the circumpolar deep water properties. So then the question becomes, what's the ultimate impact of that change as that water is potentially, some of it is advected onto the shelf. And then through shelf processes and cascading off the shelf, the question becomes, does it impact on water masses which we really care about, like Antarctic bottom water? So lots of open questions there, which we're hoping to follow up. In fact, we're doing, we've got an ocean model at NOCS, which is run up nearly up to date, which we're looking at and planning to do some trajectory analysis with it, etc., to explore this question further. So I think before I come on to storms, I'm going to pause for a minute, check that you're all there, drink my coffee, and invite a question or two if anybody has any at this stage.
Questions for Simon? Maybe if people are pondering, I'll ask a quick question.
Okay.
You've showed this really interesting relationship between sea ice cover and heat loss. To what extent is that sort of hardwired into the reanalyses?
Hardwired into the
I mean, in the sense that they assume there's no heat loss through ice, and so they build that into their.
Yeah, it's not. They don't assume there's no heat loss through ice. There is some parameterization of the heat loss through ice, and I dug into the underlying model for the reanalysis. So depending on the for each grid cell, you have a fraction of ice and and a fraction of open water, and a calculation for both. So yes, I think the major control is the amount of ice. As soon as that ice is not there, the reanalysis is going to say, right, I haven't got 80% ice cover anymore. I've got 60% ice cover, and so it's going to increase the heat loss accordingly. So I guess in that sense it's hardwired, but then that's attempting to be a simulation of what's really happening. I think in the real world. It'd be good. There's all sorts of studies to be done. Studies with coupled models and so on. Studies with better model, better representation of ice to really explore the processes in more detail than we've done here. The limiting factor is if you're concerned about process, is how well the reanalysis represents those processes. Of course, yeah.
Thanks.
Okay. I've managed to read my coffee so I can carry on, but if there is a question, I'm happy to take it. If not, I shall just plow on. I think I'm not sure how long you want me to talk for. I think I've got about another 10, 15 minutes left. Is that about right?
That sounds good, yeah.
Yeah, okay. And so the final aspect of our analysis is we wanted to see what the atmosphere was doing, what the atmospheric response was, if possible. Now, this is a very hard thing to do, and you run into all sorts of problems with trying to establish causality, etc., which are not fully resolved, but we've gone as far as we can in this analysis, and I'll try and convince you in the next few slides. So first of all, we asked the question, is there an increase in storms, which is some way co-located um, with the with the regions of strong heat loss. So in a simple-minded way, the sea ice has failed to regrow. You've got this massive increase in heat loss to the atmosphere. Um, you might imagine that that could then lead to some destabilization of the atmosphere and increase in strong wind events. So first of all, we just used a fairly simple measure of the storm activity by taking a threshold exceedance. So taking the number of days, we're now working with daily ERA5 data, um, with winds exceeding 10 meters per second. We did the same thing using a different metric, I think 95th percentile, but essentially got similar results. But here we're just trying to see if there's any co-location of increased wind events, increased storm activity, if you like, with the increase in heat loss. So the top plot here shows the storminess in June, July 2023, according to this metric. And the difference is shown in the bottom plot from the long-term climatological mean. And we can see in these areas of strong heat loss that there is indeed an increase in the number of storms. And there are some significance lines in there. The contour levels are 95% significance. Averaged over, or not averaged over the region, but the increase is up to 7 days per month. So quite a noticeable increase in the number of strong wind days. And also, I said, right, okay, so partly because we had to do this for the reviewers, but also it's just there to sort of back up what we're saying. Those are the ERA5 results. Here are the results if you take the mirror reanalysis instead. So very similar pattern of increase in storminess. And then an alternative metric is actually a 90% percentile. Again, a very similar pattern. So there is a pattern there. There are more storms in the regions where there's a greater heat loss to the atmosphere. But then the question becomes, okay, well, what causes what? Is there, it'd be quite unusual for it to be this way around, but is there a sort of a localized concentration of storms at particular locations around this in the outer ice region, which is breaking up or which is driving extra heat loss? Or is it the extra heat loss is increasing the number of storms? Now, this is difficult to answer without doing some model experiments, but what we've tried to do is then go down to look at whether there's a lag of one with respect to the other. So the point of this analysis, this part of the analysis, is to try to establish that the first thing to happen is the increase in the heat loss, and then the increase in the number of storms is delayed with respect to that increase in heat loss. So what we've done here is we've taken one of the areas of strong increase in storminess. This is the part of the northern Weddell-Sea box. We can see this is the significance level. We can see the number of days with high wind conditions has increased in this region by about 6 to 7 days per month. And then if we take that box as a whole and we form a cumulative sum of the heat applied to the atmosphere and the cumulative sum of the number of storm days, we can from early June, we can see that there is an increase pretty much straight away in the heat loss in 2023, the solid red line, compared to the dashed red line, whereas the storms take a lag with that by about 3 to 4 days, 3 to 4 day time scale. This right-hand plot is the same thing, but it just shows it on a longer time scale through June and July to see how this develops subsequently. So it does appear to be heat flux leading the increase in storm activity, but we're going to have to do some model experiments and also do some storm tracking as well to really unpin this. So the storm tracking will tell us where the storms are generated to some extent to really follow up on this question. What we have done is look at it also for the Northern Ross Sea. So you might say, well, that might be a freak of the Weddell Sea, that the storms appear to lag the increase in heat loss. But we obtain a very similar result from the Northern Ross Sea. So again, this is now the region we're interested in, the increase in storms in this area. And the cumulative heat flux rises up, diverges from climatology pretty much straight away, whereas the number of storms only increases after about 3 to 5 days or so. Okay. Okay, so now I've gone through most of the results we obtained and try and build a schematic picture of what's going on to help people. This was the schematic from the news and views in Nature, which went along with our article. You can argue about it a little bit. I didn't input this schematic, I just saw it when it appeared in the news and views. It makes it look like all of the sea ice is over the shelf, which isn't the case. So this sea ice should be a long way further out, or really the shelf should be ending about there, something like that. And you have the winter sea ice normally a long way out and marginalized around the edge. And what we're saying is in 2023 is that sea ice has retracted, so it should be about halfway out, and we should have additional heat loss there. That's modifying the atmosphere, leading to stronger wind conditions, and it's also going to modify the ocean circulation in a way that is yet to be determined. And I'm well aware of just how complex the circulation is in the Southern Ocean from my reading of various papers. And this is, again, a nice slide from the Bennett's review, and it shows the different water mass layers. So I think we've got circumpolar deep water in there. And what we're saying is that about 60 south, that's where these boxes are, about 55, well, yeah, it's about 60 south. We've got a doubling of the winter heat loss to the atmosphere. So the question then becomes, how does that impact on what's going on at depth? And how does it impact on if it's advected in this direction or partially advected in this direction, for example, in the Weddell Gyre? How does it then subsequently impact on what's going on the shelf and the mixing processes of those dense shelf waters to form AABW? And what timescale does it do that as well? As I said, we're hoping to try to get answers to some of those questions using a model. But this is our model at NOC, just a quarter degree run of NEMO. And that model is showing for 2023 a sea ice concentration anomaly in winter, which is quite close to that which is observed, which is encouraging in the sense that we will be able to use it to study the impacts out here. But of course, we're well aware that it's not going to do a particularly good job when we get onto the shelf, because you need high resolution, you need a model which really captures those processes. From talks I've heard, you really need to go probably to this access model, the Australian model, to represent what's going on there and get the water mass formation or the dense water formation correctly. But what it can tell us, our model, hopefully, is what pathways, at least in the early phases, the new water which is formed out here is following. Is it just moving off and then going north? And in fact, the reason it's is it just going north, or is a substantial part of it going to recirculate and come into the region where it could cause some changes? So that's the question we'd like to address. Now, I probably used up way too much time. So these are kind of, in some ways, a little few filler slides, so I'll go through them quite quickly. Basically, this is partly to advertise some earlier work I did a couple of years ago, where I was not looking at the sea ice, but looking away from the sea ice at the more open ocean, Southern Ocean. This is in a nice review paper associated with a meeting of the Royal Society a couple of years back. And without going into details, there's a heat flux asymmetry between the Pacific and the Atlantic Indian sectors of the Southern Ocean. This is a long-term climatological mean, and you can see that the Pacific sector tends to have much stronger heat loss from the Atlantic Indian sector, and people like JB, Saleh had looked at this in the past in terms of impacts on mixed layer, etc. And we've developed a metric for this difference. You can read more about it in that paper. But my question is, as we're modifying the sea ice substantially down here, we're modifying the air-sea interaction processes. Is that going to have a far-field effect, not that far away actually, and impact on the heat loss regimes further north, and modify in some ways this metric, this difference between the two hemispheres? I will skip that slide in the interest of time, but I will advertise another area which is also of great interest to me, and that is the relative role of heat flux and ocean heat transport convergence in causing ocean heat content anomalies. And we did a lot of work on this in the subpolar North Atlantic a couple of years ago, where we essentially, using observations and using models, we worked out at an interannual timescales the strength of surface flux anomalies and the strength of heat transport convergence anomalies, because we wanted to answer the question, what was the relative importance of the two for setting interannual variability in the ocean heat content in the mixed layer. And with this sort of figure, you can nicely separate out regions where the surface flux is dominant, i.e. these sorts of regions, and where the ocean transport convergence term is dominant. These were the results we got. It was pretty much even split between the two. But the reason I'm showing that is we now want to try and extend that, well, partly to the Southern Ocean in general, but also trying to see if changes to what extent the sea ice changes then enable surface fluxes to dominate heat content variability. And in the absence of good observational data under ice, we'll be doing this probably with a coupled model analysis. Okay, and then finally, what's happening right now? How has the ice evolved since 2023? I realize as I'm showing this, but these labels are wrong. I've just seen that they say 2013, 14, and 15. It should be 2023, 2024, and 2025. So the red line is what we've been looking at all along. It's the record low in 2023. Towards the end of 2023, it's still a pretty low value. And then we go into 2024, the green line, and that one starts off closer to the mean, but then we have another year of low sea ice conditions. And right now, I'm looking at the 2024 data to see what impact this has on the heat exchange and storm activity. I don't have any results on this as yet, but I draw your attention to the blue line here, which is 2025, not 2020, 2015, 2025. The year started a month or two ago with pretty close to normal sea ice conditions, but over the last couple of weeks, there's been a significant reduction in the sea ice as this melt season accelerates. And this was yesterday, I think, I did this plot. So 2025 is about to exceed the melt in 2024 and may yet exceed the conditions in 2023. So we may be looking at another record low year. This has actually caught the news over here. So I was talking on BBC in the UK. BBC is the main news outlet, and a reporter there has picked up on this. And these are his own figures. Actually, he's generated from NSIDC data, and he's noted that the amount of Arctic ice cover is at a record low. The Antarctic ice cover or sea ice cover is pretty low as well. And when you sum the two together, this plot here shows the global sea ice amount is now lower than these two earlier years and any earlier year in the record. And we care about this for many reasons. But if you think about the sea ice as a whole, there's a nice paper by Despair et al. Last year, which is looking on much longer time scales from the early 80s, mid 80s through to probably a couple of years ago, I guess. And according to their analysis, as a result of reduction in albedo, sea ice has lost about 14% of its natural cooling effect on the Earth climate system. So obviously that's a further concern for ever increasing global heating. And of course, this is more looking to future work. And I thank Sarah for pointing this paper out to me, Carranza et al. I'm aware that it goes beyond that. Our analysis is on heat fluxes. And I haven't really addressed any carbon questions. Haven't really ever done any proper carbon research. Maybe that will change at some point. But there's this very nice analysis, which I think you've heard about in this seminar series previously, which shows the storm-induced CO2 flux anomalies in a model analysis, and then from observations, I believe, on the right. But my point is that if we're increasing the number of storms as a result of sea ice decline, then potentially we're also increasing the CO2 flux anomalies. and we're increasing outgassing again from the southern ocean. So that's another reason to be concerned. Okay, I've reached the end. I'll let you read the conclusions and I'll take a break there and invite any questions.
Thank you, Simon. Questions? It was great food for thought. I'm sure people have
Sorry, I
lots of
pressed.
questions.
Okay, okay.
Um,
I
I
can see
guess,
it on my screen
oh yeah,
from.
yeah. Roger Samuelson has his hand up, so let's let Roger go ahead.
Thanks. Yeah, very interesting. Nice talk, Simon. I
Thank you.
wondered, with respect to the winds that you're using to gauge the storminess, are those boundary layer winds, and are you taking into account what we know about the coupling of sea surface temperature to boundary layer winds?
Yeah, it's very simple. Those are the 10-meter winds from the Era 5 reanalysis. Um, I would have liked to have done a more extensive analysis, looking a bit higher up as well. But yeah, at this stage, it's just restricted to the 10-meter winds.
Okay, thanks. Yeah, that's something to be aware of, that there's sort
Yeah,
of something on the order of a half to 1 meter per second increase in 10-meter winds for a degree of SST, something on that order typically. Of course, I
right.
don't know if it applies in this area under these conditions.
Okay, thanks for that. I mean, I'm very aware more generally of a need to bring an atmospheric scientist on board or for somebody else just to do their own analysis in terms of the atmospheric response because I'm not an atmospheric scientist. Um, but yeah, yeah, and to do some storm tracking. In fact, I did talk to Sergei Gulev about this and some of his colleagues, and he was quite keen to do something on that. But yeah, I need to follow up with him.
Rick Danielson has a question in the chat, and he says he can't use his mic, so I can read it. He asks, is there
Okay.
any merit in the question of why it took until 2023 to see a rapid decrease in sea ice cover in the Southern Hemisphere? Is the anomaly in processes related to inertia in productive sea ice formation prior to 2023?
It's probably a question for somebody else, but I think I'm not a sea ice person either, but I think what really it's not until 2023 things started to change in 2016 in terms of the summer sea ice. So we've had several events there and a reduction since that time. I mean, then the question becomes why did it take until 2016? And people have produced ideas as to why there was a slow increase or a flat line prior to that time to do with various things with freshwater supply and so on to that region. So there is some literature out there. Yeah, I haven't really answered the question there, but I think it's one which needs following up. In my head, what's going on in 20 well, so how I see the situation is we have this a long time scale preconditioning, if you like. The ocean is warming. We know this. The Southern Ocean has warmed, common with much of the ocean. So that is not favorable to sea ice formation. But I suspect that we have, so that's partly driving the longer term trend the trend since 2016 of declining ice. But then superimposed on that, we have particularly strong events in the one in 2016, the one in 2022 summer. Both of those were summers, and then 2023 winter. And at least the most recent of those two seem to have a strong atmospheric component as well. So it's those. Perhaps there's been an increase in the frequency or duration of northerly winds over some of these outer sea ice regions, and it's the fact that you have advection of warm air over the region, which is now causing these dramatic changes in sea ice. Then the question becomes, why has the atmospheric circulation changed in the last few years? And then you need to go to things like the zone wave number thing, the wave number 3 pattern, and so on. Yeah, so those are all things which are worth looking at. I hope that covers in some way what you might be thinking of. See another hand
Thanks.
up,
Yeah,
Qidong.
Qidong.
Yes, I just want to add some information about how much we can trust reanalysis. I'm not trying to prove or disprove your results, and I'm just to add some information. We don't have any, at least I don't have any in situ observations around the Antarctic to
Yeah,
validate reanalysis, but I have done something in the Arctic. So if
yeah,
we can draw analogy, maybe there's some useful information. So we use a sail drone in the Balfour and Chukchi Sea, and we
yeah.
compare the sail drone observed air sea fluxes to three reanalysis you use, the MERA-2, ERA5, and INSAP. And we found, generally speaking, they're pretty good, but occasionally they have a very large errors, and the magnitude of errors is larger than two or three standard deviation.
Mm.
And my conclusion is if you use monthly mean, probably they are good. They're pretty good. But if you want to identify on a daily basis the synoptic variability, then probably we have to be very careful.
Yes, I think that is a very valid point. That's good to know about that work. I mean, I've also in the past, we're not in ice covered regions, spent a lot of time looking at surface flux buoy data, for example, in the Irminga Sea, and also with Sarah and co-workers at the OOI mooring upstream from Drake Passage, and also the one south of Tasmania. And you're right. I mean, the reanalyses can capture quite a bit of the variability, but occasionally you'll see events which are not picked up at all. I think that's more of a concern, and I think from the work in the Irminga Sea, in particular, that's a concern where you have what's the right word? Smaller scale wind features like tip jets in the Irminga Sea. It's very hard to accurately represent those in the reanalyses, although they have some success. But if we're talking about the impacts of a warm air intrusion, and that warm air intrusion is quite large in scale, I think the reanalyses will capture that part of it. And the fact that we're seeing all three reanalyses capture it gives me, perhaps misplaced, but gives me some confidence there. I think if they were not doing so and they were just getting a lot of noise in those larger scale features, we would have seen we would have seen greater disagreement between the patterns of heat loss obtained from each one. So yeah, what we need are more moorings and more data or some moorings at least, to get something to put a handle on the accuracy of the reanalyses.
And maybe some satellites too to help get
And
everything
satellites
together.
too, yeah. Thank you for picking me up on
Everything.
that, Sarah. Yeah.
Um, let's see, there's a comment in the chat from Johan at home who says, who mentions a preprint out on Sailor data.
Well, I'd be interested in that, yeah. Johan, I've met you yet. Johan, haven't I? Where is he? I can't see him.
Yes. Hi, Simon.
Hi, Johan. How you doing?
All good. Yeah, no, we have a preprint out. But
fantastic. I'm going to check that out. I'm trying to click on it now.
I could ask a question because you touched on the zonal wave pattern 3 around here. Because I was thinking of, I mean, it's quite an unfair question because you don't have storm tracking, so
go for it. Yeah,
difficult to know where they're going. But since you have this figure as well, if it's a case of just more storms, circumpolarly, because here we see that there are some regions that experience fewer days as well. If there's a shift in the storm tracks as well, or is it a combination of both?
I don't know. I said, the biggest, the burning question is what happens when you do a storm track analysis for that winter. And I really I'd like to do it myself if I can find the right people to work with, or I'd like somebody else to do it. But I don't have an answer for you. I agree, it's a really important thing to address. Sorry, I can't be more specific on that one.
It's great, thanks.
But I can see your paper here. I should probably have a look at that in the next couple of days. So thanks for pointing that out. Great to see that sail drone data worked up.
Other comments or questions? maybe if I can finish up with one sort of open-ended question. Chidong raised questions about the Arctic, and one of the things that we hear a lot about in the Northern Hemisphere is polar vortex effects and how climate change can lead to a stronger polar vortex and more storms coming from the Arctic that get further south and disrupt
Yeah.
things more. Could there be an analogous effect with the very different land-ocean configuration in the Southern Hemisphere? Could climate change still lead to just more variability in that sort of form that could account for some of what you're looking at?
Yeah, good question. And then you maybe want to go away and look at the AR6 report and see what was said in terms of projections there. Yeah, I can't see why. So, if your argument is that to some extent, polar vortex or whatever you want to call it, or position of a jet stream or waviness of a jet stream is affected by that meridional temperature gradient, and that weakens and is important in the northern hemisphere, then why shouldn't it be important in the southern hemisphere as well? Yeah, good point.
I guess what that might go to is that these spots that you've identified of extreme heat loss, if that were the sort of scenario that was helping drive this, could be sort of randomly distributed and show up somewhere else in a different year.
Oh yeah, I think they will change. Yeah, that's something else I'm thinking about as well. Yeah, partly because I've looked at 2024. It's it changes from year. It can change from year to year, and in some ways, I don't know if I want to say this or not, but I tend to. It's difficult because because I'm primarily an oceanographer and not an atmospheric scientist, and I work in an oceanography institute. The tendency is to always want the oceans to be playing a strong role in the process. But I suspect that there's a lot of atmospheric influence here, and that atmospheric influence is manifesting itself in terms of different regions being affected in different years. If it was due to a pervasive ocean warming, then we might expect the same regions, the regions of greatest sensitivity, if you like, to that warming to be the ones which light up year on year. But that doesn't appear to be the case, at least from this very limited sample we have over the last sort of 7 or 8 years, where a handful of events have occurred. But there's a lot of mileage, I think, in asking the question: how will we separate out the likely impact of ocean changes on the sea ice and the likely impacts of atmospheric sea ice? Atmospheric warming, and can we see fingerprints? Do they have different fingerprints, and can we make progress that way? Yeah, good open question there, but it's going to stay open.
Well, great. Lots to think about. Thank you so much for a really great talk and great discussion. Thanks everybody for participating. And
yeah, thank you for the great questions. I'll take them all on board, and I hope to see some of you. I'll be talking about this in Vienna in EGU in a couple of months' time. So maybe see
people
some of you.
Can go ask the same questions again.
Yeah, I still won't have answers. Okay, lovely to see everyone. Take care now. Bye.